Hi y'all, in this video we're going to look at using first and second derivatives. The first thing you should remember is the relationship between a function, a first derivative, and a second derivative and their graphs, such as the function increases when the derivative is positive, the function decreases when the derivative is negative, function is concave up when the derivative is increasing and the second derivative is positive, and the function is concave down when the derivative is decreasing and the second derivative is negative. So we're going to add some definitions, some vocabulary before we get started. The first word is critical point. A critical point is where the first derivative is zero or does not exist. This could indicate a local maximum or minimum on the function graph. We should add that on there. Max and mins will always be referring to the function graph. The second vocabulary word is local maximum. A maximum for part of the graph. So you might have a graph that has something like this. So this part right here, this like mountaintop, would be considered a maximum. It's a local maximum. It doesn't have to be the maximum for the entire graph, just for part of the graph. So that's where the slope changes from positive to negative, or where the function changes from increasing to decreasing. So in reverse, a local minimum is a minimum for part of the graph. So if we looked at this graph, a local minimum would be here. It's kind of that valley shape, that U shape. And that's where the derivative changes from negative to positive. And then our last vocabulary word is inflection point. And this is where the second derivative equals zero or does not exist, and the graph changes concavity. That's really important, that and there. The second derivative can equal zero without a change in concavity. So what does that mean? It means that's where the function changes concavity. So it would look something like this, where you change from concave up to concave down. That would be an inflection point. The second derivative would be negative there, and the graph changes concavity. Okay, so in this first example, we're given a function graph, f of x. You should always look at the label of the graph before you start the problem. So we want to locate max and mins and critical points and inflection points. So on a function graph, a max and a min is just that valley and that mountain shape. So we have a max here, and we have a max here. And then that min is just that valley shape. So we have a min here. Okay? So critical points are also the max and the mins. Those are the same thing. So you can also call those critical points because that is where the derivative equals zero. You have a horizontal tangent line there. And then to find inflection points, you want to estimate where does the concavity change. So the graph starts out concave down, and then somewhere roughly right about here, it now changes to concave up. So that would be an inflection point. And then it stays concave up, till about here. And again, it switches to concave down, so that's another inflection point. And then the graph stays concave down, so there's only two inflection points. In the second graph, we're given a derivative graph. So this is going to change where we look for things. Max and mins are where the derivative equals zero. So now we're looking for where does the derivative cross the x-axis. So my max and mins are going to be all of my zeros on my derivative graph. And so then the question is, these are all my critical points as well, because that's where the derivative equals zero. So the question is, these are all critical points. How do you tell if it's a max or a min? So if you remember, we talked about a maximum is where the slope goes from positive to negative. So here, my slope is positive, and then my slope is negative below. So this would make a maximum. On the function graph, the slope would be positive and then negative. At the next zero, the graph is negative and then it switches to positive. So that's a minimum because the slope is negative and then it's positive. So we get a U shape. And so we just continue on like that. This graph switches from positive to negative, so that's another maximum. This point switches from negative to positive, so that's another minimum. This one switches from positive to negative, so that's a maximum. And the last one switches from negative to positive, so the last one is also a minimum. So you can use the sign of the graph to determine max and mins. Okay, so inflection points are where the second derivative equals zero. So that's going to be where the first derivative has a horizontal tangent line. Or you can think about max mins. So the max and mins of the first derivative are where the second derivative equals 0. And so those are the inflection points of the original graph. So we have 1, 2, 3, 4, 5 inflection points, because that's where the slope of the slope equals 0. Okay, in this graph, we have a second derivative graph. And notice all they asked us to find is the inflection points. When you have a second derivative graph, that's all you can do. So again, an inflection point is where the second derivative equals 0. Since this is a second derivative graph, we are looking at where does this graph cross the x-axis? Where does it equal 0? And so that would be all of your zeros. They would all be inflection points. So just a couple of warnings. Not every critical point is a local min or max. So in this graph here, this is the graph y equals x cubed. In this graph, the first derivative is 0 at 0. That has a horizontal tangent right there. But you'll notice that there is no min or max there. And then also, another warning, the second derivative equaling 0 does not automatically mean you have an inflection point. And we can call that a potential inflection point or a pip. So if you look at y equals x to the fourth, so the first derivative would be 4x cubed, and the second derivative would be 12x squared, excuse me. So where does 12x squared equal 0? Well, obviously when x equals 0. But if you look at x equals 0 on the original function graph, there is no change in concavity there. This graph is concave up everywhere. So you have to be careful with inflection points. Just because the second derivative equals 0 at a point does not necessarily mean the graph changes concavity. You have to check for that.